All right, so we are going to look at our Exam 1 review problems, and this covers Chapter 13 and Chapter 14 in our Cengage textbook. So I've numbered over here, number 1, we are looking at a 10.7 molal solution of NaOH. We're given the density and at the temperature of 20 degrees. We want to find the mole fraction, the weight percent, and the molarity. Okay, so if we have a 10.7 molal solution, that means that there's 10.7 moles of NaOH present in 1 kilogram of water, right? Because molality is moles, so little m is moles of solute over kilograms of solvent. So let's look for the first thing, mole fraction. So we need moles of solute over total moles. All right, well, we know moles of solute, that 10.7 tells me the moles of solute. Now we need to figure out how many moles of solution we have. We know that we have 1 kilogram of water. So kilograms, we know is 1 kilogram is 1,000 grams. We can go grams to moles. We can figure out how many moles of water we have. Now, we just need to figure out how many total moles. I know how many moles of solute I have. Then I just need to do solute plus the water to get the total moles. So 10.7 divided by that 55.5 plus the 10.7 to get 66.2. So our mole fraction would be 10.7 divided by 66.2 to get 0.162 with 3 sig figs. The next part, the weight percent, or often called the mass percent. That means we want, remember, percent is always part over whole, just like this fraction is part over whole, but that's moles. We're looking at weight or mass percent. We want mass of part divided by mass of whole, and then times it by 100. Percent means times it by 100. So if I look at that solute, I was told 10.7 moles of NaOH. Well, if I know moles of NaOH, I can get to grams of NaOH. So I'm just finding the molar mass, 1 Na, 1 O, 1 H. It's about 40 grams. So moles to grams. So I now know the top part, the moles of the solute. Now I need to find the total mass. Well, up here, I know the total moles, right? I can find total mass. And actually, if I know the mass of an NaOH, I just need to add the NaOH plus the water. And I know up here I had a kilogram of water, which is 1,000 grams. So 1,000 grams of water plus 428 grams of NaOH would give me my total mass of the solution. So then we just need to do 428 divided by 1428 times by 100. So our mass percent is 29.97%. And then molarity. What is the units for molarity? Molarity is moles per liter, right? Moles of NaOH, which we know. Liters of solution. Okay, so now this is where that density comes in handy that we were told. We know the density is mass divided by volume. So how do we find for volume? I also sometimes like to use this little circled guy here. Density is mass divided by volume. So you cover up what you want to find. Density is mass divided by volume. So how do we find volume? Well, it's mass divided by density. Mass divided by density. We know the mass. The mass of the solution we just found was 1428 grams. And we know the density of the solution we were told was 1.33 grams per milliliter. So let's find the volume. That divided by that gives me 1,074 milliliters. But remember, molarity needs to be in liters. So move your decimal back 3 spots, and now we can finish. Moles divided by liters to get the concentration, 9.96, capital M, to stand for molarity. All right, we're moving on to number 2. The vapor pressure of chloroform, so we're given the vapor pressure and the temperature at that vapor pressure. We want to know how many grams of testosterone, we're given the formula, and the molecular weight, must be added to, we're given grams of chloroform, to reduce the vapor pressure to 171.03 millimeters of mercury. And we know the molar mass of chloroform. So let's see what we're doing here. We're going to use Raoul Raoult's law. Now if we look that up, delta P of the solvent is equal to our mole fraction times P naught of the solvent. That's our pure solvent vapor pressure. P is our vapor pressure. Okay. So we're just going to rearrange this equation. We're going to solve for X. So divide both sides by P naught. So delta P divided by P is going to give me that mole fraction. We're just going to put that on hold for a minute here. So let's find that delta P. I'm going to take that 173.11 minus 171.03. So I got 2.08 over my pure solvent. We were told it was 173.11. So that is equal to X, right? That's what we saw for. Now X, that mole fraction is 0.012. Now we can say that X is equal to the moles of solute over the total moles. That's what a mole fraction is. Okay, so I'm going to say 0.012 is equal to the moles of solute over total moles, which would be the moles of solute plus the moles of the chloroform. Now we were told that it was added to 248.1 grams of chloroform, and we know the molar mass of chloroform, so grams divided by molar mass would give me moles. So this is what we're unsure of, right? Now, I'm going to reduce this, or I guess consolidate. So I'm going to solve for that, which gives me that 2.078. All right, and then I'm going to flip this equation around. So 1 divided by 0.012 to get this into my numerator here. Mole A over mole A is 1 plus 2.078 over mole A. 1 divided by 0.012 is 83.33. Subtract 1 from both sides, leaving me with 82.33 equal to 2.078 over mole A. And then I can rearrange this and say the mole A is 2.078 divided by 82.33 to get 0.02523 moles. And that's moles of testosterone. Now, I know the molar mass of testosterone. So if I can say 1 mole of testosterone is 288.4 grams, those moles will cancel out, leaving me with grams of testosterone. Feel free to take a minute, pause the video, go back, look at the math, and make sure you get to the same place. Let's look at number 3. Number 3, I gave you a different KH value where you didn't have to do any conversions, or I gave it to you in molarity per millimeters of mercury since our pressures were given to us in millimeters of mercury. You could have derived it. This is easier. So, look at number 3. We were given the pressure of the oxygen. We were given the new KH. Now, we know that solubility of the gas is equal to the constant times the pressure of oxygen. So all we need to do here is, we got to make sure our units match. 1.66 times 10 to the negative 6, that's molarity over millimeters of mercury times millimeters of mercury. Those will cancel out, leaving me with just capital M. So the solubility giving me 6.64 times 10 to the negative 5. Now we want to know what mass of oxygen can dissolve in 1 liter of water. So remember, molarity is moles per liter. Well, I can get rid of moles. We know this is for O2. So 1 mole of O2 is 32 grams of O2, leaving me with 2.1 times 10 to the negative 3 grams of oxygen in 1 liter. Moving on to number 4, we want to know the boiling point of a solution. We have 15 grams of urea, given this formula, in 0.5 kilograms of water, and we're given the boiling point constant for water. So let's see what we have. We're going to use our boiling point equation here. Delta T is equal to I, our Van Hoff factor, times K times the molality. And we know that this delta T, we know the boiling point of water. The normal boiling point is 100. So that change in temperature is the elevated boiling point minus 100 is equal to I. Now urea, we're assuming that I is 1. And then molality. So we're given K. We know I. We need to look and see what molality is. Remember, moles of solute divided by kilograms of solvent. So let's take our 15 grams of urea. We can get from grams to moles. Finding the molar mass of the urea, which is 60.06 grams in 1 mole. So I got 0.24975 moles. We were told that we had 0.5 kilograms of water, so moles per kilogram. All right, so that gives us our lowercase m, molality, 0.4995. So now we're just going to plug that in for m. There's our m, there's the constant that we were given, there's I, which is 1. Now we just need to find that boiling point. So plug and chug, found that the elevated boiling point was 100.26. Number 5, we're looking at the following aqueous solutions, 4 different ones. We want to know the highest boiling point, the lowest freezing point, and the highest water vapor pressure. So we've got our non-electrolyte, non-volatile, non-electrolyte here. So we're not even taking that into consideration because there's no ions. But if I look at barium bromide, potassium bromide, and cesium carbonate, what I need to do is take this molality and I need to look at, well, how many ions are in solution? So in this case, I have 3 ions in solution. So that will give me the total molality of ions in solution would be 0.3. In here, KBr, there's 1, 2, so that's why I multiplied by 2 to get that molality in solution. 0.12, and there's 1, 2 cesiums and 1 carbonate, so 3 ions to get 0.36. So the greater the molality, the higher the boiling point, leaving that cesium carbonate with the highest boiling point. Lowest freezing point, same thing, it has the highest molality. And letter C wanted the highest water vapor pressure. And we know that the lower the molality, the higher the vapor pressure. So that would be our very first solution here. And number 6, similar question. We want to rank these solutions in order of increasing melting point by ranking them from smallest to largest. Assume that the ionic compounds dissociate completely into ions in water. So let's look at these guys. I've got my sodium sulfate, so 1, 2, 3 ions. Sugar, remember it's not an ionic compound, so we're not doing it for that one. Sodium chloride has 1, 2 ions. Calcium chloride has 1, 2, 3, so times 3. And we can see here that our greatest melting point would be the sodium sulfate on down to the lowest, which would be our non-ionic compound, so the covalent compound of sugar. And then we would rank these. So this would be the biggest, and then the calcium chloride, and then the sodium chloride, and then our covalent compound. Number 7 tells us that we have 5.88 grams of Na2CO3 and is dissolved to make 250 milliliters of a solution. What is the molar concentration of the sodium carbonate? And what's the molar concentration of the 2 individual ions? So if I know grams, I can get to moles by finding the molar mass. So I added up 2 sodiums, 1 carbon, 3 oxygens to get 106. So I have moles of Na2CO3. Now remember, molarity is moles divided by liters. So I took my moles of sodium carbonate and divided it by that 250 milliliters, which is 0.250 liters. to get a concentration of the Na2CO3 of 0.218. Now, to find for the individual ions, I need to dissociate this compound here. Na2CO3 is going to break into 2 Na plus ions and 1 CO3 ion. So CO3 is a -2 charge, which is why there's 2 NAs, right? 2 pluses and 1 -2 gives me a neutral compound. Okay, so now we just need to look at our mole-to-mole ratios. If I know the concentration of the Na2CO3, and I know that for every 1 mole of Na2CO3, there's 1 mole of CO3, that means that I'll have the same concentration for the carbonate ions. And again, starting with the concentration of sodium carbonate, for every 1 mole of Na2CO3, there's 2 moles of Na+. So that Na+ ion concentration is going to be double that, 0.436 molar. Let's look at 8. 8 says if we dilute 50 milliliters of 1.5 molar hydrochloric acid to 450 milliliters, what is the concentration of the dilute acid? This is just a nice M1V1 equals M2V2, or you might have used C1V1 equals C2V2 for the concentration of the original times how much of the original, the volume, or the molarity. The molarity is the same thing as concentration. You just might have used different variables. So I'm just going to plug in. I was told the original concentration and how much I took of it, and I diluted it to 450 milliliters. I want to know that concentration. So now we just simple algebra, divide both sides by 450 to get M2 by itself, which is 0.139 molar. That would be the diluted concentration of that acid. Let's look at 9. We're told that we are dissolving 45 grams of camphor, and we're given the molar mass, in 425 milliliters of ethanol. We want to find the molality, the mole fraction, and weight percent. Okay, so let's do molality first. Little m, remember, is moles of solute over kilograms of solvent. Well, we know grams, we can get to moles. So that's just a grams to moles conversion using the molar mass. So we know the top number. We need kilograms of solvent. Well, we were told that we had 425 milliliters of solution. And we were also told the density of that solution, ethanol, we were told was 0.75 grams per milliliter. Well, if I need kilograms, kilograms is a mass. I know volume and I know density. So remember, if I want mass, I'm going to cover this up. Mass is density times volume. So let's take our density that we were given times volume. Remember, those milliliters will cancel out, leaving me with just grams. But I need kilograms for that denominator. So I just moved my decimal point back 3 spots to get the moles over kilograms. And I should get 0.886 little m for molality. Let's look at B. Now, the mole fraction, remember, is the moles of solute over total moles. Well, we found that moles of solute, right, 0.2956 moles. I need total moles. So I knew how many grams of ethanol I just found in that last problem when I did density times volume. So if I need moles of ethanol, I'm going to go from grams to moles of ethanol. And I got 7.237 moles of ethanol plus the moles of my solute. That'll give me total moles. So top divided by bottom, I get my mole fraction. And last, the mass percent or the weight percent. So mass of solute over total mass times it by 100. The mass of solute, we were told we had 45 grams of camphor over, we need total mass. So I'm going to take 45 grams plus that 333.625 grams times it by 100. We should get 11.9%. Looking at number 10, we're using Raoult's law again. So the relative lowering of vapor pressure and looking at mole fraction of the solute. So P naught minus P, that gives me my delta P over my P naught is equal to the mole fraction. So what do I know? I'm trying to find the mass of glycol. So again, I need to find moles of glycol, and that would be my moles of glycol, because I'm gonna find out. I know what this is because I know mass of water, and mass of water I can get to moles of water. So I can find this part. I just need to find the mass of glycol added. So let's start plugging in what we know. We're given the two pressures, the original pressure and the what the pressure changed to. So I'm just going to subtract those two divided by my original pressure. That gives me my mole fraction, which is equal to this. Mole fraction, remember, is my moles of solute over total moles. So that's the moles of solute plus the moles of the solution. Okay, so I can find out what this guy is going from grams. Well, 2 kilograms is 2,000 grams, grams to moles. So I know how many moles of water, which is mole B. I'm going to set it up just like I did before. There's my mole fraction, 0.1308. I should have put that in there. All right, let's make this usable. So I'm going to flip this fraction around, which means I need to flip this guy around. That gets me 1 divided by 0.1308, 7.642 is equal to Na over Na is 1 plus 111.11 over Na. So we'll reduce this, subtract 1 from both sides. That leaves me with just this fraction. And then I can solve for the moles of my solute, which is 16.7 moles of ethylene glycol. And from there, moles to grams, because we were told ethylene glycol is HOCH2CH2OH. Molar mass is 62 grams. So I had 1,035 grams of ethylene glycol dissolved in water. Looking at question number 11, we are looking at rate laws. We're given this reaction, and we want to determine the order of the reaction for each reactant. So first, I'm going to let's look at NO. When we want to find NO, we have to look at, well, where does the other reactant stay the same? We don't want that variable to impact it. So I'm going to look and go, oh, hey, look, from trial 1 to trial 2, that concentration stayed the same. So let's look and see what happened then to NO between trial 1 and 2, and what happened to the rate between 1 and 2. So I'm going to do some division here and do trial 1 divided by trial 2. So from trial 1 to trial 2, my rate doubled. From trial 1 to trial 2, the rate quadrupled, went up by 4. So then I asked myself, well, 2 raised to the what power equals 4? And 2 raised to the power of 2 is equal to 4. So this is the order for NO. Now let's look at H2. So if I want to know the order for H2, I have to look and go, well, where does NO stay the same? And it stays the same from trial 2 to 3. So let's look at what happens to H2 during the second to the third, and the rate from the second to the third. So I'm going to do 0.143 divided by 0.286, and I got 0.5. So its concentration was cut in half. And let's see what happened to the rate from the same two trials. 0.0418 divided by 0.0835, the rate was also cut in half. So to find the order, we ask ourselves, well, 0.5 raised to the what power equals 0.5? And that would be to the first power. So this is the order for H2. So we would write our rate, and say rate is equal to K times the concentration of NO to the second power, to the second order, times the concentration of H2 to the order of 1. Then we want to write, that is writing the rate equation for each. So A, second order for NO, first order for H2. Here's our equation, and C wants us to find the rate constant. Now, to find the K, you can use any of these trials, 1, 2, 3, or 4. I usually use 1 just because it's listed first. So I'm going to say for the rate, I'm going to use the 0.166 is equal to K times, this is the concentration of NO, so I have to come up here and use this value that given for the concentration of NO squared times the concentration of H2 to the first power. Now we just solve for K, and I got a rate constant of 6.31. And as far as units, our rate, we look up and it's moles per liter, so that's molarity over seconds. So molarity over seconds is my rate, divided by, this is molarity squared and that's molarity the first, so divided by molarity cubed. So that will cancel along with one of these m's, leaving me with seconds inverse, molarity inverse to the second power. All right, let's look at number 12. We are given this graph, natural log of CH3NC, and then that's my y-axis, and time is my x. So if I look at our little cheat sheet here, we can see that the natural log of A over time is a first order reaction, and we're given what that looks like, how that's set up in a y equals mx plus b setup. So y equals mx plus b, that would be the natural log after time, a certain amount of time, is equal to negative kt plus the natural log, the initial concentration. And it wants, so we already said that it's first order, the rate law is equal to K times the concentration of CH3NC. The rate constant is negative K, which is my slope. And for my 2 points being used, I used the 8,000 for time and the 4.5 or negative 4.5. So to solve for K, my slope, I did the natural log after time t, which, so I used the negative 5.75 minus the negative 4.5 all over the change in time. So I did the 8,000 minus the 2,000 seconds. That gave me negative K. And then, of course, I want to take the opposite of negative K to get K. So 2.0 times 10 to the negative fourth inverse seconds. And then the last question says, how long does it take for half of the sample to isomerize? And we already figured out that it was a first order reaction. And first order, we know the half-life is 0.693 divided by K. So since we already solved for K, we can just do 0.693 divided by 2 times 10 to the negative fourth. And it would take 3,465 seconds for half of that sample to isomerize. Number 13, we're given a reaction between ozone and nitrogen dioxide. Ozone and nitrogen dioxide. It's first order for both, so I'm going to rewrite it. The rate is equal to K times, here we go, nitrogen dioxide first order, ozone first order. So there's our rate equation. If the concentration of NO2 is tripled and O3 is not changed, so if we triple NO2, then the change in the reaction rate will be tripled. Now, the next one says, if the concentration of ozone is half and nothing's happening with NO2, if it's halved, then the rate of the reaction is halved. Moving on to number 14, we are told that the concentration of NO2 was measured as a function of time. The graph of 1 over the concentration of NO2 versus time. So 1 over the concentration versus time. So it must be a second order reaction. Gives us a straight line, so we're told our slope, 1.8 liters per mole seconds. So given that information, what is the rate law for this reaction? So rate must equal K times the concentration of NO2 to the second order. What's the rate constant? Well, so for a second order reaction, we're just going to plug it into our equation here. So I already subtracted the original concentration on both sides here. So that'll give me my y equals mx plus b set up here. And our k, which is our m, is the slope. 1.8 liters per mole seconds. And again, that's because m in the y equals mx plus b setup, m stands for slope, and this would be our y equals mx plus b. So this is the m, and we know m is slope. We were told it's 1.8, so k is 1.8. Looking at number 15. 15, we're told that we have the decomposition and carbon tetrachloride is a first order reaction. So first order reaction, here's what we're going to be using. The natural log of A is equal to negative KT plus the natural log of A original. So I've got that written right here. And we want to solve the value of the rate constant. So I'm going to rearrange this to solve for K. So I'm going to subtract a natural log of original A from both sides, so natural log of AT minus the natural log of A. We were told our original and our concentration after time t. Divide both sides by time, and I'm going to take the negative time just so I have K by itself, 2.54 minutes. And we should get 4.83 times 10 to the negative 3 inverse minutes. For number 16, we're told right in the problem that experiments show that this reaction is second order for NO and first order for Br2. So that's our rate equation. Rate is equal to K times NO squared, Br2 to the first power. How does this change if the concentration is changed from 0.0022 to 0.0066? So if I divided 0.0066 divided by 0.0022, that tells me that it is tripled. So I've tripled the concentration. So for Br2, since it's to the first power, the rate will triple. Now for NO, if we have the concentration, so 0.024 to 0.0012, so if we have it, it's going to decrease by a factor of 4 because it's second order. All right, let's look at number 17. So 17 gave us a whole chart of trials looking at carbon monoxide plus nitrogen dioxide and looking at the rate, the initial rates. And so what I did was I saw, CO stayed consistent from 1 to 2. So let's look at what happens to NO2 from trial 1 to 2 and what happens to the rate from 1 to 2. And when I divided 2 divided by 1, 2 divided by 1, I saw that the concentration doubled and the rate doubled. So because the concentration and the rate both doubled, NO2 is to the first order. NO2. Then I found the trials where NO2 stayed the same, which was trial 1 and trial 4. So what happened to CO for trial 1 to trial 4? It looks like, so I did 4 divided by 1, that it almost doubled, 1.96. And when I did the rate, the fourth rate divided by the first rate, it got the same, the 1.96. So almost doubled again, but those are the exact same. So since they're the same, it's first order for CO as well. So my rate would be, rate is equal to K times CO times the concentration of NO2, both to the first power. Then it wants us to calculate the rate constant. All right, so I'm going to use trial 1, like I always do, plugging in the rate is equal to K times the concentration of CO, I use that concentration, times the concentration of NO2, which I use this guy, both to the first power, solving for K, and I got moles per liter per, is this hour? Yep, moles per liter, hours, molarity squared. So I could also reduce this, because moles per liter, that would be capital M over H, that's molarity per hour, and then I am also dividing by M2. So that could cross off one M and one M, so I could just say 1.40 inverse hour, inverse molarity. Same thing. All right, and for the very last question, number 18, we are told that the activation energy for a reaction is 260 kilojoules per mole. We are given the temperature and the rate constant for that temperature, and we want to find the rate constant at 850 Kelvin, and we are given gas constant R. So that tells us, especially since we were told activation energy, we need to use our Arrhenius equation. The natural log of K2 over K1 is equal to negative activation energy over R, and then times that by 1 over T2 minus 1 over T1. So I'm just going to plug in everything that I'm given, and then we just need to plug and chug and reduce. I reduced, let's see, this, my negative activation energy over R, and my 1 over T2 minus 1 over T1, which then went down to 2.299. Natural log of K2 over 0.0315. Obviously, to get rid of the natural log, we need to use Euler's number, so that gets rid of this. So then I would do E raised to the 2.299. Then I'm at simple fraction here. 9.967 times 0.0315 should give me K2. 0.314 inverse seconds.